Okay, so let's continue. The next talk would be Erin from the US, who will talk about scalable automatic machine learning. Erin, please take the stage.
Okay, I'll give people like a few seconds to get seated. All right. So my name's Erin LeDell, and I'm the Chief Machine Learning Scientist at H2O AI, which I'll tell you a little bit more about on a slide. But today I'm going to talk about scalable automatic machine learning in H2O. I think it should be H2O in R as well, but the focus will be R, but H2O is a multi-language platform. So the agenda is I'm just going to talk a little bit about what does the term automatic machine learning mean, and then I'll talk about how we define AutoML at H2O, or what our implementation of that is. And then I will give you some practical tips for using it. It's pretty simple to use, but there's a few things to be aware of. And then I will, if we have time, I'll show you some of the tutorials at the end, but otherwise I'll just point you to them so that you can try it out in R when you're done or while you're listening to the talk. And then if you want to download these slides, that's the URL that you can do that at. And I will have a link at the end of the talk too if you missed that for some reason. Okay, so intro to automatic machine learning. So I guess this is just how I define it. It's not a sort of well-defined academic discipline yet. I mean, it sort of is, but it's also just kind of a generic term that people use differently. So I like to divide it up into 3 categories of tasks that all combine together into making an automatic machine learning system. So the first thing is just, this is required in any machine learning process, is you have to prepare your data in some way, first to make it able to be read by machine learning algorithms, so just formatting your data into rows and columns. And then this could include any type of other data preparation, like imputing missing values or encoding categorical values. And with encoding categorical values, there's a lot of different ways that you can do that. So one-hot encoding is kind of the default way that people do that, but then there's all sorts of sort of fancy tricks that are used by people like that are good at Kaggle, that know how to make good use out of categorical features, and especially high cardinality categorical features. So once you have your data set, then you could generate a whole bunch of models generally. So the goal, I guess I should state what I think the goal of automatic machine learning is, and I think it's something where you give it your data set and you specify maybe something that you care about, like a loss function or a metric that you want to judge your models by. So you say, here's my training set, here's what the response column is. I'm trying to maximize AUC, and I want to do it in a certain time limit, usually. So I think you could run machine learning models forever, and that's one way to get a good model. But generally, with automatic machine learning, you either want to specify a time limit or some sort of metric-based early stopping to stop the process. And so once you have a large number of models, and I'll talk about all different ways to make models, one of the things that you can do optionally at the end is to ensemble them together. And there's a lot of different ways to do ensembles as well, so I'll talk a little bit about that. So just to kind of break down some of these into more specific items, I mentioned for data processing, this could include all sorts of things that you typically already do, but then we could include sort of automatic feature engineering in that pipeline as well, or automatic feature selection or dimensionality reduction or anything like that. And so for model generation, then there's a couple ways that people do this. So one is grid search. So typically random grid search is what people would do, or If your goal is to optimize a single model like a GBM, instead of making a big ensemble, then you might want to use something like Bayesian hyperparameter optimization, which is a technique for training a bunch of models, but you each time learn something about whether or not that model helped maximize the metric that you care about, and that's why it's called Bayesian, because you're sort of learning from the prior knowledge that you've been gaining as you go through. So that's another technique. I'm not going to talk about that too much today. And then when you have a model like a GBM or some model where it's an iterative training process, you can also tune the number of iterations in a single model. And then ensembles, which is one of my favorite things personally, is there's a couple different ways to ensemble things. One, you could average models together, but that doesn't usually give you the best performance. So the technique that I like to use is called stacking, and stacked ensembles. There's a lot of different names for it, superlearning. And then there's another technique called ensemble selection, which is more of a greedy approach to adding individual models into an ensemble. Okay, so that's kind of just a broad overview. That's kind of a short, broad overview of the whole field. But so now I'm just going to introduce the H2O AutoML. And then just to provide some context, let me just tell you what H2O is if you're not aware of what it is or why it's different from other machine learning platforms. So H2O, in the context of the R world, is an H2O R package. So you can just download that from CRAN. And one of the things that is unique to H2O is that these algorithms that we have written all from scratch are distributed. So you can run them on your laptop, or you can run them on like a really gigantic cluster. And the goal was to create a library that could sort of be infinitely scalable to whatever data size. So that's never something that you should have to worry about. So if you need more memory, you just add more nodes to your cluster. But you shouldn't use cluster computing if you don't have to. So if you have a laptop and your data fits in memory, that's the best way to use it still, or just a single desktop. So anyway, the algorithms are written in Java, but we don't force you to deal with Java. So you can use the R package or the Python package, or we actually have a web GUI as well. And one of the other things about H2O is that we designed it to be sort of a production level machine learning library that makes it easy to deploy models into production. So those are all in Java code. You can also save binary models if you're not deploying them to production. So that's kind of just an overview of H2O. And so we have all of these machine learning models in H2O and a lot of infrastructure like grid search, early stopping, performance metrics, all of this cross-validation, all the stuff that kind of goes along with machine learning that isn't actually machine learning. So we have all of that infrastructure. And then on top of that, we have built basically automated what we think is of the H2O library, like how could we automate everything so that you basically have to run one function, it will do a whole bunch of machine learning and then ensembles, and then give you kind of a ranked list of models. So right now, so this is fairly new software. It's been around for about a year. So all the H2O models do this imputation, one-hot encoding, and standardization when required for all the machine learning algorithms anyway, so we get that for free. One thing that we're working on adding now to AutoML is target encoding. So we've just added that to H2O. I don't even know that if we've publicized it yet. It's actually just in R right now. But again, it uses the scalable infrastructure underneath. And then we do random grid search, and then we tune the individual models using a validation set, and then we do stacking at the end. And that's kind of that's our process. So it looks very different from if you're doing Bayesian hyperparameter optimization. So our goal was to use everything that we have in H2O, and that's already scalable and right there. Our already created and create the best automatic version of that. And so let me just say, why do we do random grid search and stacking together? So those two techniques fit really well together because stacking does well when you have kind of a diverse model set. So a strong, diverse model, so a GBM, or maybe a whole bunch of GBMs, and a random forest, and a deep neural net, and I wouldn't call GLMs a strong model, but sometimes it's good to have those in there. And then we ensemble them together. So one way to get even more of a diverse selection, if even in addition to just using a bunch of different types of algorithms, we do random grid search within each of those algorithms so that even all the GBMs are very different from each other, and all the random forests and all the deep neural nets. So that's why we like to combine those two things together. It's also very easy to do a random grid search. So one thing about Bayesian hyperparameter optimization is that it's a sequential process. So depending on the software that you use, it can take a little bit of time between each of the model training to figure out what the next set of parameters should be. So this is kind of just the fast and dirty approach to AutoML. And just if you're not familiar with stacking, it uses machine learning to decide what the best combination of the models is. So there's a second level of learning that happens on top of the original models. So it's sometimes called meta learning as well. Oops. Okay. So anyway, this kind of just reiterates what I've already said. So, and the thing, when you run AutoML, what you get back is something that we call the leaderboard, and that's like maybe a term borrowed from Kaggle or these data science competitions where you rank all the models. And this is what it looks like in R. So just load your training data in, and if you've never used H2O before, we have just a parallelized file reader called import file, and you can also load data into R and send it over to the H2O cluster, which is usually just running a Java process running on your laptop. But that's where all the data lives, and the models live in the H2O Java cluster, so you have to get the data in there. So this function will directly load it right into there, so you don't have to convert or anything like that. And so for AutoML, these are sort of the minimum number of arguments that you would have to set. So you say, what is the training frame? So train is the training frame. And then you have to just let it know which response column you're using. There's some logic to figure out what metric should be used to optimize. If you can also rank the results by whatever metric you want, but so if it's a binary classification, it would use AUC, for example. And then the max runtime seconds, there's a couple ways to stop AutoML. One is by time. You just say run for this amount of time and stop. Another way would be max models. So you say train 100 models and then stop. And the default is that it will run for an hour. So if you don't touch anything, it will just do that. And then there's the leaderboard. This is just a snapshot of what it looks like in our GUI. So if you're running the R package or the Python package or any version of H2O, it's also running a web server in the background, so you can always go and look at your results in a web format, or you can actually train models doing that as well. And this is kind of an example leaderboard. This is just running on a small, I think, 10,000 row data set. And so you get two ensembles. So one of them is an ensemble of all the models that you've trained, and that's usually the best one. And we rank based on cross-validated metrics. So, and then the second one is designed for if you want to take this to production, you don't want probably 100 models in your ensemble. So we take the best GBM, the best random forest, the best deep neural net, the best GLM, and we actually, there's two versions of random forest. One's called extremely randomized trees, and then a regular random forest. We have one of each. And then that would be what we call the best of family stacked ensemble. And then generally, GBMs are towards the top of the list. I think our next speaker is going to talk a lot about GBMs and how great they are, and it's true what you hear. So yeah, so this is just an example. Let's kind of skip through this maybe. So before you start running a whole bunch of models, especially if you're using infrastructure that costs money. So here's just some tips. So I mentioned you should only have to specify training frame, and if you do that, we will chop off a little bit of your data, 20% of your data, to do the validation internally. So if you don't want to use 20%, let's say you only want to use 5% or no percent, then you can use the validation frame argument to override what we do. And then the leaderboard frame is something, if you want to score the leaderboard on a particular set of data, then you can use the leaderboard frame argument, but I wouldn't recommend that. I would recommend using the default, which is cross-validated metrics, because then you don't sort of waste any data just to score. So those are those two tips. So one thing that people asked for when we first put this out was how I don't want to run all these different algorithms. I want to choose which ones that I run. Specifically, if people are either saying they don't want to run the tree-based algorithms or they don't want to run the GLMs and the deep neural nets. So we have this exclude algos argument where you can turn on and off certain algorithms. So the reason why people would want to do this is if you have really, really wide sparse data, you might not want to run tree-based models on it, for example. And then I mentioned this already. It'll stop after 1 hour. And if you want it to be reproducible, you should use max models, because if you run it once for a certain amount of time, there might be a certain amount of resources available, and it will get only this much work done. And if you run it a second time, it might have more or less available and not be giving you the exact same result. And just a reminder, all the models and the data is stored in the cluster memory. So by default, when you use this H2O init, that's how you start the H2O cluster. It will give you a 4 gig cluster, and that's just kind of protect people from, using a lot of memory that they don't want. So if you want to use more, then you have to specify max mem size to something bigger. And in the future, we'll have a way to kind of clear out bad models so that you're not wasting time or wasting memory, to store them. But there's kind of a trick to that, because sometimes bad models work well for the ensemble, so you have to figure out a smart way of keeping just like the good bad models. And then you could just save the model. So they get this leaderboard, and it has all the names of the models by ID. And then if you want to save an AutoML model, you can do it the same way you save any H2O model, and it will just save the leaderboard only, or the winner of the leaderboard, so the top model, it will save that. And then I'll just point you to this link where we have tutorials, and I think that's it. So I will just leave this up here, and again, you can just get these slides later. And if you want to contribute to H2O, that would be wonderful. It's open source. And that's it. This is my contact information. So I guess any questions? I don't know if we're doing...
We are here.
Okay.
Behind you. Thank you very much for the presentation. Do we have questions from the audience? There's a question on the left. I will try to get the microphone to you without falling.
I have a question about that your framework has some relation to Frank Hutter AutoScikit-learn framework. Do you contribute to them or vice versa?
Yeah, so there's a couple other AutoML frameworks. There's not too many. Probably the most famous one is called AutoSklearn. And that there's a group at the University of Freiburg in Germany that is kind of, at least that I know of, kind of the main AutoML research center of the world. And they have, so I know the PhD student who works on it, and so we're sort of in contact, and he knows about this. So it's similar and different. So they use Bayesian hyperparameter optimization, And then they use ensemble selection. So they kind of use the reverse of what we do. And so one thing that's important with AutoML development is that we're just making this stuff up. So we have to measure if it works or not. So one of the things that we're doing is I'm working with some of those people, actually through the OpenML. OpenML.org is a benchmarking website. And so we're going to work on some sort of benchmarking systems so that we can compare all of these techniques and then, iterate once we realize what works and what doesn't work. So we actually don't really have benchmarks. So a few internal ones, but that's it.
That would be a very interesting project to do some cross-benchmarking for all the auto-learning solutions. Okay, thank you very much.